What's up, guys? Today we're going to do sum and difference identities. We've done quotient, we've done reciprocal, we've done Pythagorean identities. So today we're going to take cosine and sine, and we're going to do and tangent, and we're going to do sum and difference identities. So let's go ahead and get started with the cosine identities. So what we can say is this, guys, that the cosine of alpha plus beta, two different angles, is going to be equal to the cosine of alpha times the cosine of beta minus the sine of alpha sine of beta. Now, you may be wondering why when I added these two angles together that I subtracted. That is part of the identity of cosine sum. Where there's also a cosine difference. Cosine of alpha minus beta, again, two different angles, not the same, is equal to the cosine of alpha, cosine of beta, plus the sine of alpha times the sine of beta. Alright? Well, there are also some different identities for sine as well. And we say that the sine of alpha plus beta equals the sine of alpha cosine of beta. Since we're adding here, you would think we would subtract, but that's only for cosine that we change these signs up. For sine, they're the same. Plus cosine of alpha sine of beta. What's up, Mr. Simmons?
So full.
Can you tell we're doing this during lunch?
How come this one started with cosine and that one started with sine?
Because that's the identities. Cosine, sine starts with sine.
Oh, see, it keeps the alpha beta in order.
Ah, yeah, the alpha and the beta stays in order.
Okay, very good.
So alpha, beta, and so forth and so on. Then we have the sine of alpha minus beta equals the sine of alpha cosine of beta minus the cosine of alpha sine of beta. So kind of interestingly, when we're in cosine, when we're adding on the left side, when we're adding the two different angles together, we subtract in the identity part on the right. But in sine, when we add, subtract, we subtract. Just got to swap those signs in that cosine sum and difference guy. Alright, so interesting, that's interesting. Now, what do we use this for? Well, what we're going to use this for is when we're trying to find exact values of angles that are not readily available on the unit circle like we've been doing. You know, pi over 4, pi over 3, pi over 6, pi over 2, 2 pi over 3, all of that stuff. Well, now we're going to have angles that are not necessarily on the unit circle. Well, they are, but it's not the main angles.
We only have 16 common angles on the unit circle.
That's right.
And this will give us a procedure to get exact values of trig functions of angles other than those 12. Won't work for all angles, but for some it will.
That's right. Then we have the tangent of alpha plus beta. Yes, we got to deal with tan, sine, cosine, and tan. And the tan of alpha plus beta is going to be equal to the tangent of alpha plus the tangent of beta over 1 minus tan alpha tan beta. Is how that works. Tangent of alpha plus the tangent of beta. When we're adding, we add the top, subtract the bottom. 1 minus the tan alpha, tan beta. Then we have the tan of alpha minus beta is equal to the tan of alpha minus the tangent of beta divided by 1 plus tan alpha tan beta. That's how the tangent works. Now, another way you could really do tangent, guys, if you were finding the tangent of alpha plus beta, is you could go up here, and remember tangent is
sine divided by cosine, isn't it?
Sine divided by cosine. So if we're adding, we go up and we do the cosine on the top of the addition stuff.
Sine on the top.
Sine on the top. Sine on the top of the addition stuff, and the cosine of the bottom of the addition stuff. Or if we're subtracting, we could do the sine subtraction on the top and cosine subtraction on the bottom. But this is the shortcut to doing all that, because that would kind of get long. You'd end up dividing fractions, reciprocating, multiplying. This kind of takes
And
that
your
all
alpha
out.
and beta are going to be common angles that we already know exact values of.
That's right.
And you guys already know the tangent values for those common angles.
We can only find exact
either-
values of angles
Right.
that we already know.
Exactly. So you're going to be plugging in zeros or ones or root threes or root 3/3s for those.
Okay. So let's kind of look at an example right quick. All right. So let's do, for example, the cosine of pi over 3 plus pi over 4. How would that look as an identity of alpha plus beta? So what I want you to know here is the pi over 3 is going to be my alpha, and the pi over 4 is going to be my beta. So we're just going to replace that. We're going to replace that into the normal. Now if you remember, if I go back, we said the cosine of alpha plus beta is cosine alpha, cosine beta, minus sine alpha, sine beta. So when we're adding in cosine, we're subtracting on the right side.
And it's
So-
cosine, cosine, sine, sine.
that's right. So it's the cosine of pi over 3 times the cosine of pi over 4 minus the sine of pi over 3 times the sine of pi over 4. Okay? So that is how we would write all of that out. And we're going to give you guys some practice over this. So then let's just go ahead and find the exact value of this. Because, you know, the exact value of pi over 3 plus pi over 4 is going to give us some other angle, but it's not on the unit circle. These individually are, but not added together or subtracted. So let's look at this. So the cosine of pi over 3
Is 1/2.
is a half. And I use parentheses.
Okay.
And the cosine of pi over 4,
Root 2/2.
root 2 over 2, minus sine of pi over 3,
Root 3/2.
and the sine of pi over 4,
Root 2/2.
root 2 over 2. So I'm multiplying fractions together, and then I'm taking the difference of those. Remember, when you multiply straight across. Numerator times numerator, denominator times denominator. So 1 times the square root of 2 is the square root of 2. 2 times 2 is 4, minus the square root of 3 times the square root of 2.
And how would you do that?
Is this, you multiply the radicands together.
Oh, okay.
Yeah, it's called the product property of radicals.
Okay. So you
And then
small-
2 times 2 is 4.
Okay. Very good.
Now, we could actually combine this. You don't have to now. I would definitely not mark it wrong in an exam. But since these are common, I could put them over 1, just like we did when we were simplifying and solving that way. So that's how we would approach that. So why don't we look at the sign of the difference of these two
Okay.
right quick. All right. So the sign of the difference of these. So let's find the sign of pi over 3 minus pi over 4.
All right.
All right. So that would be the sign, treating this as alpha and this as beta. The sign of pi over 3 times the cosine of pi over 4. Again, applying that identity. Minus, we got to keep the same signs in the sign.
Signs are the same.
Signs are the
Signs
same
are
in
the
the
same.
sign. So minus cosine. Why do I keep writing sign there? It's crazy. Minus cosine of pi over 3 times the sine of pi over 4. So the sine of pi over 3 is going to be the half. No, square root of 3 over 2. Square root of 3 over 2. And the cosine of pi over 4, everybody knows, is root 2 over 2. Minus the cosine of pi over 3 is going to be a half. So you're taking the sine of pi over 3, if it's square root of 2 over 2, the cosine's got to be a half. And then the sine of pi over 4, again, is square root of 2 over 2. And we get the square root of 6 over 4 minus the square root of 2 over 4, which you could write combined over 4. Now I got a question, Mr. Simmons.
All right.
Can I just add the square root of 6 minus the square root of 2 to get the square root of 8?
No.
There's no sum property of radicals?
No, there's not. You can think of this as, this might be overkill.
Well, okay.
These are terms with different, the exponents are the same, but the bases are different. That would be like adding x squared and y squared. You can't do it.
You can't do it.
They are unlike terms.
Unlike terms.
These are unlike terms.
So that's it. We're done with that. That is the answer, exact answer. Now, of course, we could put this all in the calculator, get a decimal equivalent, but the
Right.
goal here is to find exact
That's
values.
correct.
And since these are irrational, the calculator is going to round them off, and cut them off,
Yep.
and all of that. So let's do a 10 one, shall we? Whoa! Whoa! Hi-yo! Okay, anyway. So let's do the tan of pi over 3. Let's do a plus. It doesn't really matter. Plus pi over 4. We're just showing you some examples here, guys. So remember that that's going to be the tangent
Tan
of
plus
alpha.
Tan plus tan.
The tangent of pi over 3 plus
Tangent of pi over 4.
tangent of pi over 4 over
1 minus their product.
1 minus the product of tangent of pi over 3 times the tangent of pi over 4. So once I get tan pi over 3 pi over 4, I just sub those numbers in there and we're good. So what's the tangent of pi over 3? Well, it's going to be the square root of 3 over 2 divided by a half, which is just the square root of 3. The tangent of pi over 4 is going to be
1.
1. 1 minus, see that 1 just comes down, the minus just comes down, the tangent of pi over 3. So now I'm multiplying these two numbers together to get the square root of 3, right? But should we simplify this in terms of a conjugate, Mr. Simmons?
Why not?
So why don't we, to undo the radicals from the bottom, we multiply by the conjugate.
But if I multiply, there's also an integer here. And if I multiply by root 3, that'll just give me root 3 minus not minus 3.
We'll still have a radical.
Yeah, so I have a radical.
So if we're going to simplify this further, we would have to do this. 1 plus the square root of 3, the conjugate of this. The conjugate is the opposite sign, remember that. And then 1 plus the square root of 3, which will be equal to, when we FOIL, if you will, first order, we're multiplying two binomials. Square root of 3 times the square root of 3 is the square root of 3. The square root of 3, excuse me, the square root of 3 times 1 is the square root of 3. The square root of 3 times the square root of 3 is
3.
3. 1 times 1 is
1.
And 1 times the square root of 3 is
Root 3.
Alright. So the bottom, 1 times 1 is
1.
1 times the square root of 3 is
Square root of 3.
negative square root of 3 times 1.
Negative square root of 3.
And negative square root of 3 times negative square root of 3
Negative
is
times negative is a positive, so that would be negative 3.
negative 3. Alright. So now I've got two square roots of 3's. Now remember on the previous example how he said they were unlike and we couldn't add them together? Well, now these are like.
Yeah.
So that's 1 times the square root of 3 plus 1 times the square root of 3. That's going to be
2.
2 times the square root of 3. And then 3 plus 1 is
4.
4. Yeah, maybe. Something like that. And then what happens to these, Mr. Simmons?
Well, they just cancel out.
They're opposite signs. And then 1 minus 3 is negative 2. Now we usually don't like to leave that negative. And we could actually simplify this further, Mr. Simmons, if we did this. If we factored a 2 out of the top, square root of 3 plus 2, over negative 2, the 2's would cancel, and I'm going to move this negative up, but when I'm dividing both by negatives, it means I've got to change these two signs.
Right.
So that's going to be negative the square root of 3 minus 2. Whoo-wee! How was that for fun, guys? So there's a little bit to the tangent ones. Be careful with those. Make sure you watch your signs. We brought in the idea of multiplying by the conjugate of the denominator to get rid of that radical. We have simplified. We talked about how to add, subtract, and multiply radicals. And we've reduced to its simplest form. So I believe that's all we need to do.
Go back to the formula page.
Oh, go back to the formula page. Oh yeah.
Do you want to talk about the condensed form?
Yeah, we can talk very quickly about the condensed form, guys. Instead of having two separate formulas for cosine, sum and difference, and 2 for sine, and 2 for tangent, we can actually condense those into one where it's plus minus, and plus minus, and plus minus. So let's talk about that. And, oh yeah, we need to do one more thing as well when we get done. Alright, so what we can say then is the cosine of alpha plus minus beta, that's saying alpha plus beta and alpha minus beta, is equal to the cosine of alpha, cosine of beta, and instead of plus minus we do minus over plus. So when we're adding we subtract, when we're subtracting we
add with cosines.
That's right. Sine of alpha, sine of beta. And then the sine of alpha plus minus beta is going to be, remember, sine starts with sine, sine cosine, but plus minus we still.
The sines are the same.
That's right.
Same sines.
Cosine alpha, sine beta. So sine, cosine, cosine, sine, alpha, beta. And then the tan of alpha plus minus beta is going to be the tangent of alpha plus minus the tangent of beta over 1 minus plus tangent of alpha, tangent of beta. And in fact, this is probably the way you'll see it in some other textbook.
It's how it's written in our textbook as well.
They won't do it separately like we did, but that's okay, because we did it separately.
That's right.
The only thing I want to do next is I want to come back, I want to quickly talk about one more thing, and we'll be done. I know you guys are ready, you're probably asleep by now. We said the cosine of pi over 3 plus pi over 4. Do you think we're going to see it as the cosine of pi over 3 plus pi over 4, Mr. Simmons?
You know, every time we've taken sine or cosine of an angle, it's always been a single angle.
A single angle?
Yeah.
So if I were to add these two together to get the single angle that we're taking the cosine of, we would take pi over 3 plus pi over 4. We can't add those together. The denominators are not the same, Mr. Simmons.
Well, can we find a common denominator?
I bet we can. So I'm going to multiply the left by 4 over 4 to get 12 as my common denominator, and the right by 3 over 3. That's 4 pi over 12 plus 3 pi over 12, which is 7 pi over 12. So the way you're probably going to see this in your textbook or some other textbook is not the cosine of pi over 3 plus pi over 4, but it will be the cosine of 7 pi over 12. What you're going to eventually have to do is start here and know that it's these two angles or some other similar angles to get 7 pi over 12.
The sum or difference of two common angles.
Sum or difference of two common angles. We'll also be doing this with some degree measures as well. We just showed it with radian examples. So that's pretty much it. Now, of course, we would do the rest of the stuff, and you guys saw that example. We're good to go?
I believe so.
Good luck, guys. Watch this video. We're out of here.